Okay, so you should have your cell packet with you right now. That is what our lecture is going to be over. And I'm actually going to break this up into two parts. So we're not going to cover the entire packet, and this will be the same packet that we come back to the following week when we have our next lecture. So make sure that you guys keep it handy and that you have that with you when you go to listen to both of those lectures. So the first few chapters that we've had to go through have been chapters that are kind of the foundation, the building blocks for getting to the actual body systems. So moving into the cells, we're now getting into the parts of the body, how they're working. And the reason that we take one whole chapter to focus just on the cell is because it is the basic unit of life. You can have organisms that have absolutely everything that they need in order to do all of their jobs, to keep themselves alive, to reproduce in one single cell. And then you have other organisms, obviously, which are much more complex and are going to take, like us, trillions of cells in order to accomplish that same thing. So it's a very wide range when we talk about the cell as to how complex it is, how many cells you have involved, but it is the very basic unit of all living things. So if you look at that first slide, it talks about it being the basic unit of life. And within the cell, part of our focus, and in fact, the second lecture that we have is going to be over the organelles. The organelles are tiny little structures that you have inside of a cell. So if you think about the human body, we have our internal organs, which do all the jobs that we need in order to keep us alive. And the cell's going to have the same thing, just on a much smaller version. So we need to be able to take in oxygen and put that oxygen to work, so do the cells. We have to digest things, so do our cells. Everything that we basically do as a function, the cells have to do as well. And that is going to be the job of the organelles in order to get that done. When we look at the cell, one of the things that a lot of people really don't consider is that the cell is much more than just a building block. And a lot of times that's kind of all people really think of it as being is you put a bunch of them together and you make an organ or you create a bone, but you're building some structure within the body. And while that's very true, it's only half the story. Because when we talk about cells, cells are going to also be tiny little factories. They are going to take all of the things that we put into our body and they are going to break those things down and reassemble them into what we actually need. If you really think about it, when we put food into our body, when we put drinks into our body, there's really not much in those things that is part of our body. There is no food that we eat that is going to just be able to go straight from the food as we put it into our system and become part of our body. It has to transition. And that's what the cells are going to do. They take that food, they break it down into its individual nutrients, and then they rebuild that to create the tissues that we need, the muscles that we need, and all the other structures within our body. That's a big job. They have to work 24 hours a day to make sure that they are constantly manufacturing all of the products, all the materials that we need to keep our body alive. And so it's not just a building block piece, it is also very much a factory producing and making sure that anything that we need is going to be on hand and ready to go. When we look at the outside of the cell membrane is going to be made mostly of lipids. And initially, when you see this, or if you've, or when you hear about it, that in itself doesn't really mean too much. It's made out of fat, and a lot of times people gloss over that fact and just keep moving on. But when you really stop and think about it, the fact that those cell membranes, the surrounding around the cell, that surface is made out of fat is very important. And I say it all the time when I teach anatomy, and you have to remember it. Nothing in the body happens by chance. If we have a structure, if a particular molecule is made out of something, there is a very specific reason for that. Nothing is just because. And so when I say that the cell membrane is made out of lipids, there's a very important reason tied to that. And in the case of our cells, the reason it's so important that that cell membrane is made out of lipids is because it's kind of like mixing oil and water. They don't like each other, so they're not going to interact. And you have that kind of barrier between the two. So when we equate this or put this to the cell membrane, now we have a situation where you can put these cells in a liquid environment, which is how most of our cells are going to spend their entire lives, is in a liquid environment, and they're not going to dissolve, because just like oil and water don't mix, those lipids and um, the liquid environment of our bodies is not going to mix either. And so it makes sure that the integrity of the cell is always going to be kept because it's made out of that fatty substance. So that is a very important detail. The last point on that first slide talks about stem cells. And stem cells are a hot topic issue. There's a lot of research being done with stem cells, and there's a lot of controversy as to whether or not we should actually be doing that. And the reason for that is where we have to get stem cells from, or where we can get them in a large amount. Now, the important thing to keep in mind is that everybody has stem cells, no matter how old they are. They have stem cells in their body. I have stem cells right now. You guys all have stem cells. But typically, when we hear the word stem cells, we think of embryos. And that is a very true connection. The reason that we tend to kind of gravitate towards thinking about embryos when we talk about stem cells is because they are going to have a much higher volume of stem cells compared to an adult. Because as an adult, most of my cells have already been assigned to a task or to a job. So, with all of my organs being formed, I have my cells that were already programmed to become my heart, that were programmed to become my stomach, all my other internal organs. Now, I still have some stem cells that are embedded, but they're already in my tissues, my existing tissues. So I have stem cells for my skin, but they're embedded within my skin cells. I have stem cells in my liver, but again, they're embedded in that liver. When you talk about an embryo, it's a little bit different situation because they have clusters and large bundles of cells that have not yet been given their directions as to what body part they're going to become. They're like blank slate cells. They could become absolutely anything. And so that's why we typically get stem cells from embryos, is because you can harvest a large number of them and they're easier to get to because they're not already embedded in other existing tissue like an adult's would be. Now, the problem with stem cell research, or the concern that some people have with stem cell research, is that in taking those stem cells from an embryo, obviously that embryo is not going to be able to go to term and ever be born. And so people have very strong opinions on that issue. But with stem cells, the benefit to looking at those particular types of cells is that because they have not been given their direction on what they're going to become within the body, if we could figure that out, if we could figure out exactly what happens, that that cell that is a blank slate all of a sudden knows, okay, I'm going to have to become a heart cell, or I'm going to have to become a brain cell. When we can figure out what causes that programming to happen and that differentiation, then a lot of medical illnesses, a lot of medical disorders and diseases could potentially be fixed and corrected. And so that's why we put a lot of time and effort into that research, because right now scientists don't know. As much as we know about the human body and about the cell itself, they don't know what causes that to happen, what causes a cell to go from not having any direction to now transitioning and developing everything it needs to become part of a particular organ. So it's information that would be very beneficial, but at the same time, it's still a huge mystery. If you look at the second slide on the bottom of page 1, it talks about the plasma membrane. And one thing that we tend to do in science is we tend to take one structure and give it a bunch of different names. And the cell membrane is true to that as well. So sometimes you'll see it as the cell membrane. Here it's the plasma membrane, the fluid mosaic model. A lot of different ways to refer to the structure that you have surrounding the outside of the cell. Whichever one you are comfortable with, that's fine. Go ahead and use it. Depending on past instructors, you might have heard of it a particular way and that just connects with you. That's fine, but just as long as you know that if you hear it in one of these other ways, that we are simply still talking about that cell membrane layer. So with the plasma membrane, it is going to basically create a barrier between the inside of the cell and the outside of the cell. And this barrier is very important because, again, if you think about the situation that a lot of our cells are in for most of their life, they are in an environment where they are surrounded by liquid. And that is how we get things to move from one point to another point in the body. But in moving things around, we're moving ions, we're moving elements, we're moving molecules. And sometimes you could potentially have things interact with each other and cause a particular reaction to happen that you don't necessarily want to have happen. So those cell membranes are very, very important because they take certain contents and they separate them from those other materials. So it creates this barrier, this gate, that is going to make sure that if you need something to be specific and held within that cell, that it is held where it's needed and it's not easily interacting with those other ions, those other elements, and getting taken into some other chemical reaction somewhere else in the body. Your plasma membrane is typically going to be what we call selectively permeable, which means it's going to regulate what gets in and out of the cell. It will monitor what's crossing that cell membrane. And in doing that, it makes sure that anything that could potentially do damage to the cell is not allowed to enter. Does sometimes it not do its job correctly and things get in and damage the cell? Yes, but it's typically very good at doing what it's supposed to and monitoring and making sure that what's supposed to be on the outside is kept out and what is supposed to pass through is allowed to pass through. Now, within the cell membrane, one of the biggest things that we're going to have content-wise is the cytoplasm. The cytoplasm is a fluid. It's a little bit thicker than water, but the cytoplasm is going to, number one, help the cell maintain its shape. So any space within the cell that is not taken up by organelles is going to be filled with the cytoplasm. And that's going to make sure that that nice round shape that we typically associate with a cell is easily maintained. The other thing that it's going to do is it's going to allow for materials that need to move within the cell to be able to do that fairly easily. Like I said, it's a gel-like fluid material, and so it helps to move stuff from point A to point B. A lot of times when I talk about cytoplasm, I will tell students to kind of consider it like the air in the room. You guys think about the room that you're currently sitting in, there's probably some furniture, depending on where you're at, some tables, chairs, things like that. And then you have this space within the room that there isn't anything. There's no furniture or other objects. And that is taken up by air. That's essentially what your cytoplasm does within the cell. All right, if you flip over to page 2, it talks a little bit more about the plasma membrane, and some of this I've already covered, referring to it and identifying that it is a barrier separating the inside and the outside contents of the cell, regulating what is allowed to pass through that cell membrane. And it talks about ions, and it's been a couple weeks since we talked about our chemistry chapter, but ions are anything that carry a charge. Could be a positive charge, could be a negative charge, but we know that opposites attract. So if you let those positive and those negatives interact at the wrong time, you get a reaction to happen that maybe you don't want. So a lot of times that cell membrane is very beneficial in making sure that the positives stay on one side of the cell membrane, the negatives stay on the other side until you actually want them to interact with each other. Go ahead and flip over to page 3. Page 3 talks a little bit more about the structure of the plasma membrane, and it focuses on the individual lipids themselves. Now, the interesting thing about the cell membrane is it's made up of all these lipids. And if you look at just one lipid by itself, it has a round head and it has 2 tails extending off of that head. The head is what we would call hydrophilic. Hydro means to, or indicates water, and philic comes from phil, which means to love. So if you actually break the word down into its meaning, it means water loving. On the other hand, those 2 tails extending off of the head are what we call hydrophobic. Again, hydro indicating water, but phobic is indicating that it has a fear. And so when we break down this word, it means water hating. So the reason that that is so important is if you somewhere on the side of your paper, and you have a picture of it too on the bottom of page 3. If you pick out one of those lipids, you can see the nice round head, you can see the two tails extending off of it. But just across from that, you'll notice that it's two layers. There's a head facing the opposite direction and two tails, and the two tails actually meet in the middle. So when we talk about the cell membrane, it's two layers of lipids. The heads face the outside of the cell and the inside of the cell, and the two tails are facing each other. So this is going to create that barrier, and you're going to have that inside separated from the external environment around the cell. So if you look at that picture, and we go back to the terms hydrophilic and hydrophobic, you'll notice that the heads are always turned so that they would be facing the liquid. We talked about the inside of the cell having cytoplasm, and that is a gel-like liquid, and that's what the heads are going to be exposed to. If you look at the heads that face the outside of the cell, again, that's going to typically be a liquid environment. So the heads are always facing the direction where the liquid's going to be. The tails, on the other hand, being hydrophobic, they hate water. They don't want to be exposed to it. So they're always turned to the inside so that they are held away from the water. Now, again, there's a purpose behind that. In having that sort of setup with the heads liking to be exposed to water and the tails hating it, there is no physical attachment between those lipids. They will hold their position just because those tails hate to be exposed to water. So they will always stay turned to the inside. Those heads will always stay turned to the liquid areas. And so there doesn't have to be any physical connection from one lipid to the next. They're not linked to each other, they're not bonded to each other. And the reason that that's so important is because now you can have other materials, other ions, tiny little particles that can easily slip between those lipids and move across that cell membrane and go from outside the cell to inside the cell. Likewise, you could have something on the inside of the cell and it could push through those lipids and go from being inside the cell to outside of the cell. So in having that hydrophilic hydrophobic setup, all the lipids stay where they're supposed to, and you have a situation where things can easily pass through the cell membrane. With the amount of material that the cell produces, I told you it's a tiny little factory, in having all of those places where things can move in and out easily makes the cell much more efficient. If you can imagine, you go to a movie theater and it is packed full of people, got 1,000 people in the movie theater, and there is one door letting people in and out. It's going to take forever to get out. But if you have 1,000 people packed into that movie theater and there are 30 sets of doors, now getting out is going to be much easier, go much faster compared to just having one door. So having all those places where little ions, little particles can get in and out without having to find a doorway, so to speak, just allows the cell to be much more efficient in getting product in and out. Now, if you continue to look at that cell membrane, there are a couple features here that we need to talk about in addition to the lipids. Now, easily, if you look at that picture, you can tell that lipids far outnumber any structure that you have, any other structure that we have within the cell membrane, and that is very true. The main component of your cell membrane is going to be lipids, but we always have exceptions to the rule. Sometimes particles or ions are too big to move across that cell membrane in between those lipids, and they have to have another way to do that. So if you'll notice, every so often you have what are identified as protein channels. So you have almost right in the middle of the picture, it talks about the protein channel. What that's actually going to do is that is going to create a passageway for those particles that are a little bit larger. If you think about a large molecule trying to pass between those lipids, you could see in a very quick hurry if that molecule was too large, how it would push through those lipids, but it would potentially rip the cell membrane open. So once you get into those molecules that are a little bit too big to pass through in between those lipids without causing damage, now they're going to resort to those protein channels. Protein channels do the same thing. They allow material to move in or out of the cell, but it's designed for those molecules that are a little bit on the larger side and need a little more help getting across the cell membrane. if you go from, so I had you looking at that protein channel that's in the center of the picture. If you move over to the left and look at that protein channel, it's almost off the picture. It's so far left. You'll notice that there's an arrow identifying that it's a gated channel, and it has two little kind of arms that are almost closing off the passageway through that protein channel. So this is another control method that your cell membrane will use to make sure that something's not getting in or out of the cell that's not supposed to enter or that's not supposed to leave. And so those gates will close down when it wants to be regulated. And in a situation where you need something to pass through, those gates will open up, allow for that exchange to happen, and then close back down when it's finished. And so that's, like I said, it's another way that the cell can regulate things going in and out. The last thing that I would like you guys to find is every once in a while you'll see they kind of have a geometric shape to them. The glycolipids, you have glycocalyx that are sporadic on the surface of the cell membrane. Those are actually going to be made out of carbohydrates. That is where that glyco prefix is going to come from. And basically, they're like little flag indicators that you have on the surface of the cell. These play a very important role as well, because if you go back to our earlier conversation, your cells, majority of them, are going to exist not only in a liquid environment, but they're going to exist in a dark environment. It's not like you're walking down the street and you look at somebody's face and you can recognize who you're looking at and the sun's shining and it's bright. That's not where your cells exist. They exist in a dark, confined area. And as they are moving about from one place to another in your body, a lot of times they bump into each other. And not having any light, not being able to see one another, so to speak, they have to have another method to be able to recognize one another so that you can tell this is something that my body made, this is something that is supposed to be here. And so those carbohydrate flags extend off the surface of the cell. So as they're bumping around and running into each other, those flags will brush up against each other and they just alert your body that this is supposed to be here. Other things that might invade your system are going to have their own carbohydrate flags. And when your cells bump into those, they don't recognize them. Now we can trigger an immune response. We can alert our white blood cells that something is in our body that is not supposed to be there, and they will start the process of checking it out and figuring out how they're going to defend our body against it. So those carbohydrate flags are very important for cell-to-cell recognition. It's how we recognize what our body made and how we recognize something that is in our body but is not supposed to be there. The other big thing that those carbohydrate flags will do is they will alert cells when they've taken, or excuse me, they will alert organs when they've taken up their space for growing. So you have a growth spurt, put on some height and things like that, and the organs become spread out from each other. Well, they need to grow as well to accommodate the changing needs of your body. And so as they start to grow, they need to know when they have taken up their allotted space and that they need to stop the growing process because they don't need to grow anymore. So if you think about, again, the situation that your organs are in, your organs don't have their own personal space. Your internal organs touch each other. They are packed in one right next to the other. There's no space where they're removed from each other or they're not touching another body part. And so it's very important that they know when they've taken up their space and they need to be done with that growing process. And that's what those carbohydrate flags do in this particular case as well. Those flags will run into each other. And when those carbohydrate flags from, let's say, your stomach and your liver start to run into each other and overlap to a certain degree, those two organs know that they have taken up their space. They need to shut down the cell production that is causing them to grow and increase in size. And you grow again, they get spaced out from each other. Those carbohydrate flags are not coming in as much contact. They'll start to produce cells to grow again until they grow, overlap one another, and now they know to shut down that process. So it's a monitoring system to make sure that your organs are growing and developing with you, but they are not growing to the point that they are taking up more space and potentially interfering with the space that another neighboring organ has or needs. So those carbohydrate flags, very important. They do a lot for the body and for the cell. And so that is why we see them on the surface of the cell. So if you move into the next page is going to start to get into the organelles. And it classifies the two different types that we have. We have what are known as non-membranous and membranous organelles, and that just means that they have a membrane wrapped around them or they lack that. And it shows you the two groups of organelles that we have, and that's actually going to move us into our next conversation. So I will take you through those organelles next time that we talk. And then if you look at the end of the packet, it starts to get into the process of cell division, mitosis. And so we will spend a little bit of time on that as well. And then that will wrap up our two conversations that we need to have on the cells. So like I said, make sure that you have that packet with you next time you sit down for the following week on our lecture then. If you have any questions, let me know. Have a good night.